if anyone wants to continue next semester with deep learning and natural language processing, there is a seminar I'm teaching at the computer science faculty, so therefore it will be very easy for a computer science guy to count this as a normal seminar. It's a seminar for bachelor or masters, and it will be applied deep learning for natural language processing. It will take place on Thursdays in Garching, but I don't have the room and the time right now. So if anyone is interested in joining the seminar, there is a Vorbesprechung, a pre-meeting. This will be tomorrow, Thursday at 2 o'clock here. Not here in this room, but upstairs in the 3rd floor next month. Good. So what are we doing now? Always this.
We did the correct code from last time. Before starting it, if you would like to start downloading the file, because it will take too long, so we can do for the second script. So if you can go to the, not to WE-Vis, yes, but to the other. Yes. If you open the pre-trained GRU. Exactly. So I beg you to go to this link here and download the file with this name. It's some gigabytes and the TU.
It's the same one that was the last week, right?
Yeah.
Some gigabytes.
It's some, yeah. And because the TU internet might be slow, it may take some time, so let's download it.
The globe.
The globe, yeah.
And this is the pre-trained here.
Yeah, exactly. The pre-trained vector from globe. Yeah. But
good. So we figured out what was the problem last time.
so it was my mistake because
that's mine.
No, I really copied the code wrong from your model. It was my mistake.
So, but the real problem was we have here in this example a very difficult structure of the text. So we have the posts. We had what we have is a list of posts. Yeah, and we want to keep this structure.
No,
it's not a list.
It is the European Union document.
Okay. So we have a list of documents.
Yeah.
And combine these documents, and then in the document we have sentences, and the sentences are lists of words. And at one point we just got the wrong order, so we were taking all the time the same word. But now it should work. So you had time to have a look at this. These are the regular libraries. It shouldn't be surprising. We already covered tokenization and the removement of characters.
Yes,
That's okay. Okay, now we load the data from the NLTK package. These are all these different parliamentary protocols from the European Parliament translated into German. We see the first sentence. Okay, what are we doing here? What and why are we doing this? What are the difference between the word to index map and the index to word?
The index map is a map where a word is mapped to a number, and the index word map is where the number is resolved back to the word.
Okay, and why do we need this?
Because otherwise they just like numbers, not words.
Exactly. So, what would be the size of our index to word map? If you take this approach on your own data, what size would you expect? Or what dimensions?
As many unique words as we have.
Exactly.
I have a question.
Yes.
And why do we need two different maps and not only one and just go from one direction to the other?
Well, it's more or less what we are doing, but we take this dictionary structure from Python.
So you only have one key and nothing
So
else.
this is a very efficient way to store the data. The data can be quite big because every unique word has an own entry in the data. So this is the whole reason that two dictionaries in the end to make fast lookups from index to word and from word to index. Just imagine you're adding new documents to your project. We can probably guess that the vocabulary size, so the length of our dictionary, the number of unique words, is increasing. Yeah, this is straightforward. But what do you think? How much is the length of the dictionary increasing when you're adding new documents?
Well, I guess we would hope that not much because we already have a representative dictionary so that we could use it for any more.
So probably the more documents you already have in the dictionary, adding even more documents will somehow increase the number of the unique words, but many of the words should already be in the dictionary. And this is quite interesting because this is something like a general law in natural language processing. It's called the ZIP law, which means that you can apply this in very different contexts. It means that the amount of new words follows very straight, something like a log normal distribution. So if you add another document, you will get from one document to the next document, the increase of words might be represented as a logarithm of the already presented words, and so on and so on. So this means that the amount of new words with every document is rapidly decreasing. And the same is true, for example, with a number of characters in words. So when you have a word that has you have the idea is you have few words with a lot of characters, and the more characters you add to a word, the fewer words there are using this many characters. And this is quite logical from information theoretical point of view, because normally we don't like to write very long words. German is a little bit different in this point, but even there, normally you don't want to write very, very long words, but you want to transport a lot of information, and therefore the amount of information that you want to transport is with just one additional character, you can add a lot of information to a word. So if you want to increase your information, and the information that you want to communicate might be limited to a certain point, so you don't have to increase many characters to a word. But this is a typical feature of many tasks in natural language processing, and it's quite useful to know this because for example, when we train such a word-to-vec thing, then we might think, I never can get all the words into the corpus. But even a very, very big corpus normally has not much more than 200,000 words. So I think
it's still a lot for computation.
Yes, but the point is, it is not linearly increasing. This is the important thing. So this means with every new document, for example, you add to your classifier, you gain a lot more flexibility because you can use the same words and in different contexts. And, the more words you have, you will get a huge set of additional contexts that you can use this classifier. So this is the idea. Okay, skip grams. What are skip grams?
It's almost a combination of two words.
Okay, two words, yes, and
So one word and its respective neighbors.
exactly.
So in this case, the neighbors.
Have we designed the window size?
Yes, it's two.
Ah,
I've done it at you.
okay. So in this case, this means what? If you have a range or a window size of 2, how do our skip grams look?
It's the respective word, and well, it's either both neighbors which were before and afterwards, or only one neighbor before, after, I don't know. And either it's the total length of 2 or it's 4. I think it's 4.
Let's say we have this, the brown fox is quick sentence. What would be the skip grams?
Also, the fox, brown fox, fox is fox quick. Right?
The brown fox is quick, then we would have the brown first skip gram, and the fox second skip gram, and there you already see that it's important not just to have the direct neighbors, because in this case it's the combination of the fox that might be very common. This would be the second skip gram, and then we would have we already have the brown, and we have brown is, and brown fox, and so on. Let's have a look at this work this time, what we have into our skip grams here.
So you take for each word 2 before, two combinations with the one before, the 2 second before, and two combinations with the one ahead and the 1, 2 ahead. So it's 4.
It didn't work. No. Sorry, it didn't work.
Let's get enough and last.
Yeah. This is the right code. And this is really strange because last time we had the same problem here as well, but when you were going, we reran it and it looked perfect. So it was really, really strange. this looks right, but zeigt uns vielleicht Skip-Gram jetzt einfach nur die Nummer der Listen oder so.
Ja, genau. Das Ganze. Okay, doch hier.
Yeah, but nevertheless, it's like. Okay, we have window size 2, so it starts with 1. Is it starting with 1 or is it starting with 0 if you take range?
With 0.
Now then this is the problem. Yeah. Let's see. So the lesson is always debug your code.
Most of you need to put subscript to the sign and so on.
This is the problem. Okay. Let's go through this for loop and see why this strange behavior comes. So what we found out, we were looking at the skip-grams and we saw that the first skip-grams that were created were always the same word. So the was together in the context with the fox with fox, brown with brown, and this is not helpful for what we want to do. So the point is we have defined a window size of 2. Yeah? If we go through this loop, the range is 0 to 2. 5. It's not 1 to 2, it's 0 to 2. Now, in the first loop, our j has first the value 0. Then we take we are starting with the second word from the sentence. So it's our I has value 1, but the first word would be 0, and we go in this case to the end of the sentence because j is already j is 0 right now. So we have j0 and I is 1 in the first loop. What is happening? Now we take the word to index map of, so we are looking up this, the second word of the sentence here, and we are looking up the index word. This is our first element, the second word. Okay, this makes sense. Then our
and this is the mistake because we want to take the word before, but we subtract 0.
Yeah.
So we take again the same word, and instead of taking the next word, we take again the same word because we are 0. So we need to replace range window size with range 1 comma window size, and then it will work. So now it should work if we print.
and it's quite fast. You know, this tiny machine.
You make screenshots of yourself.
It always happens in this.
Yeah.
Yeah. Now we got it.
Exactly.
So now our skip grams is the first word and the second word, the second and the first, which is right, the other, the second and the third, and so on. This is what we want to do. Okay, why do we need the function skipgram batch? Get skipgram batch. What is it?
When we apply data to the model, with every iteration, we only take a batch of given sizes. I think 200,000 or 20,000 or 2,000, I don't know.
Just as a reminder, why are we working with batches at all?
To overcome all of this as well.
Yeah, because we are normally in neural networks using stochastic gradient descent algorithms. So this means we are only optimizing on batches of the data to prevent falling into a local minima.
That's the one thing, and the other is that we cannot fit all the data in the model. It's really computationally expensive. So sometimes the solution is to reduce the batch time or to make it work.
Okay, this is an example of a batch.
So what are we doing here? We're training a word-to-vec model. So what should our inputs look like, and how should our outputs look like? Our x and epsilon.
Sorry, in the batches part, what x and y stand for?
Yeah, normally in machine learning, it's common to have the y character for the response variable and the x character for the predictors of the model. And in our case, we want to build the model with one x matrix or whatever, and one y matrix. And do you remember how our x and how our y in the model looks like when we want to create a word-to-vec model?
The word-to-vec is the matrix of the co-occurrence of the words, so it's the columns and the rows of the matrix. The x are the columns, and the y's are the intercepting cells.
So,
No, not exactly. So what we do is skip grams. So actually what we feed in the model, we feed a word, and we want to calculate the probability that another word appears. So our inputs are actually a matrix.
First, to think about it, our inputs are words, with one word as an input, as an x is one word. If every observation is one x and one y, and one x is one word, and y is a word that was found in the skip grams to be in a context with these other words. So we have one word mapping to another word, but we cannot map a word to a word. So all our words are encoded in pod 1 encoding. So this means we have a huge vector with the length of all the words of our vocabulary, and for each column of this vector, for each entry of this vector, we have either a 0 or 1. And this is the representation of our words that we have. We are not working with the words as words, and we cannot just work with the indexes we created of the words, because the word 35 is not in a numerical relationship to the word 70 or something. So every word is transferred into pod 1 encoding, means all x's are 0 except for 1. So if you have the word index 5, for example, then only the fifth column of all the x columns has a 1 or the other set 0. And this fifth word might be in a skip grammar together with what would be a possible combination, a very likely combination. The fifth word is probably in a skip grammar with the fourth word, and the sixth word, and the seventh, and the third. If we did it right, at least. So, and our y then would be, in this case, for this one observation, the whole vector over the length of our unique words, with only set the fourth column entry to 1 and everything else to 0. So this is how the structure is, and this is what we have in the badges, but we are taking the words in the badges and remapping them to words so that we can see what word is.
So, exactly, so we feed in our batch the number, the index of each word, and then the index is transformed in the model through one hot encoding to the vector. You click from the wrong. Yeah. Where am I? Yeah. So what dimensions does our model have in the word-to-vec model? The input?
Algebra stuff that no one
No.
in this part of the room can remember.
Do we have a mark? We said, what do we do? Our input is a vector with the length of the vocabulary, and 1 with zeros and 1 for the appearance of the word. So what's the input is a vector of dimension on V, the length of our vocabulary. And what is the output of our model?
The concurrence matrix.
Again, a vector of the length of the vocabulary
The
and probabilities inside for each of them. One probability for each word of appearing in the context of our input.
And here, the most important thing that you always have to remember is when you're working with TensorFlow. So TF, we import TensorFlow as TF. When you're working with TensorFlow, you have to define your placeholders. You have to define your variables before you can use them. This is one thing that makes TensorFlow very fast and very reliable, because here you are telling the computer how much space it should reserve for the object train inputs. And this is done by a TensorFlow placeholder, and then you define exactly the dimensions. So that's just so then we are working with a lookup table. This again, this is the important thing here. This is already a function that is implemented in TensorFlow. So this works that you enter the embeddings. The embeddings are, this is what we want to have in the end. So the embeddings are our the weights of our neurons in the neural net, and we take the train inputs as input to the TensorFlow neural net embedding loop. And what this function does is that it is very fast in dealing with big tensors to look up the connection between the inputs and the embeddings. So because for every input has a weight that goes to every neuron in the neural net. So we have a lot of embeddings that we have to deal with in this. And this is our loss function. What is a loss function in machine learning?
This is the function you want to optimize.
Exactly. So machine learning is very stupid. We cannot do any very intelligent things with it. The only thing machine learning is doing is it's optimizing the mathematical function. And we have to define the function, and therefore knowing the exact cost function or loss function, sometimes it's called loss, sometimes it's called cost, but it's the same, is one of the most important parts of every algorithm. And even with deep learning architectures, where you might not be able to really understand all the calculations that are done in every node and every wave and every layer and so on and so on. You learn a lot about the algorithm and what it is really doing when you know the cost function. And the cost function normally is very, very simple. So for example, if Facebook would just tell us what exactly the cost function, the loss function, the different algorithms Facebook is using is, then we would know a lot about the Facebook algorithm. And here, the cost function that we apply is the NCE. NCE stands for what? We covered this 2 sessions ago. Noise, contrastive, and E stands for estimator.
Estimation.
Yeah.
Noise contrasting.
So, at the beginning of the seminar, we covered, for example, the softmax optimization or loss function. This is softmax was traditionally used in such settings like we have this now, because it's a classification problem. Softmax gives us the probability that one class is the result of the calculations of the network. So normally for classification problems you would use a softmax function. But here we have it makes a lot of sense not to use softmax but use this noise contrastive estimator, because normally one word is just mapped to some few other words. So one word will occur in the context with, let's say, perhaps 100 words or so, but definitely not with 100,000 words. This is how we constructed the context. Of course, the bigger the window size is, then the bigger the context will be. But nevertheless, most words will not be part of the context. So the idea with a noise contrastive estimator is that you are taking some samples of the data where you already know that these are negative samples, that you know, I don't show the computer all the pairs. I'm not pairing my words with all the things, all the possible contexts, but only with some contexts that are given, and with some of the data where I know there is no context in it. So this is the idea that you, this is why it's called noise contrasted. You take noise, you take random noise to map your positive data against this noise. And what the algorithm learns then very fast is to differentiate between a real connection and a noise connection. And this is the idea. This can be used, for example, for face recognition and other things. And the good thing is the computer doesn't have to do so many calculations. So here we are really defining, here we were just setting up the variables for the NCE. We were defining the weights and the biases for our neural network, and here we have the real cost function.
Who wants to explain what the loss function says there? So let's go step by step.
What does reduce mean do?
So when we fit the patch, we get a loss for each observation. Okay? Reduce mean just takes the mean of all the losses in the batch. If we give 100 observations as input, we're going to get 100 errors. But we want to take one error to see how good our model is. So we take the mean. This is what the reduce mean function does. Okay, what does the function TensorFlow and then NC loss? What did it do? It gets inputs and calculates the loss.
It calculates the noise contrastive estimator.
Exactly.
So, we want to reduce the mean of the calculations of this function. And this function gets as inputs all the weights for our neural network, biases, the inputs are this number of neurons we have, our training labels, and then this is what I just explained. We define a number of negative samples we want to match our observation each time, and of course we have to say how many classes do we have in the system, the vocabulary size, because for every word we have every word is a class of it. Now comes another magic step in TensorFlow, a learning rate decay. We haven't covered this, but it's very helpful when you are doing deep learning.
So why do we have a learning rate?
What is a learning rate?
Yeah. Where does it appear?
It's to use it to optimize it, make it more appropriate.
Exactly. So it has something to do with optimization. So what did we say last time? In order to see how our weights change, we calculate a derivative. How the weights should change towards one direction when we do the backpropagation. But we don't want to change the weights too much each time. We only want to change them a little bit so we can find the optimum. And this is where the learning rate comes in. We multiply our change with the learning rate, a very, very small number, like 0.001, so that we can control that our weights change a little bit each time.
But now comes the problem. Because we are assigning random weights, or random numbers to our weights, it's quite likely that at the beginning we could do bigger jumps with the learning rate, because the weights are just random, might go in a totally wrong direction. So it would be nice if we could adjust our learning rate, if we could start with higher values at the beginning and then decrease the learning rate. Because then we can do large steps first, but are not in danger later when we are into the minimum, the local minimum, or even global minimum, to overfit our model with a too high learning rate. So this is the whole idea about the decay in the learning rate. Then it just means you can start with a higher learning rate, this speeds up the calculations, but then you have to carefully decrease the learning rate so that you're not jumping out of the optima that you have already found. And this is a very hot topic in the field of deep learning right now. Different algorithms now for designing the right learning rate. So again, we have another parameter that we might want to tweak around. For example, there are even some very successful models today where we have an increase, a very high increase in the learning rate at the beginning, and then a strong decrease. And as with all these things, no one really knows why it is better or not so good, and you just have to try it out. And if you find a new algorithm for a learning rate that somehow improves the performance on a standard machine learning problem, then you have a nice paper you can present at the next NIPS problem, if it's good. So yeah, but this is what we are doing here. And again, we have to define our variables in TensorFlow. So this is just because we are working with TensorFlow, you always have to first say what are the dimensions of the things we want to put into our TensorFlow training object. And here, now we define a decay rate, so we say we have 1,000 steps. The learning rate is quite high at the beginning, it's 0.1, and in 1,000 steps, every step we just take 99% of our given learning rate. So we are decreasing, this way. What is happening there? And now we start our TensorFlow session in this one. So this means now we have defined all our variables for TensorFlow, and then we start a session. And this means now we put real values into these placeholders and let the tensors flow around. This is why it's called TensorFlow. And now it's running, and we see our loss function.
Put the range to 500 or something, because otherwise it will run for a very long time. So we can see the results. Yeah, 200. It's okay.
Can I just rerun it, or have I?
Yeah.
So what you are, just let it run a little bit. What does this tell us? So the output comes from, where do we have it here? We say with each step print the loss. Print loss at. So what does loss at 100 means? After 100, so we had defined 2,000 steps. So this means we run 2,000 iterations over our data to train the model. This is the problem with this deep learning stuff, because of forward propagation and back propagation, you have to run it a lot of times. And in each step, we then take a batch of our data, and we define a summary here. This is for something we will show later. It's for the visualization. Write the summary into data, and then after 100 steps, so this just means if you divide the actual step by 100, and you don't get any rest of the division. So every 100 times, the session is saved, the model is saved. Yeah. So this is quite important. This means if you would stop the whole process at a certain point, you will find in your log directory still a saved model that you can use.
And you can implement the code. Now it's not like that. That opens again the saved model and starts training it from the point you stopped. So when you have huge models that need to be trained a lot of days, you can stop it for only some days and then reopen it and continue the optimization from the same point.
Exactly. So this is very important for us for you as pure Kurs students, where you don't have a computer that you can just put in a corner and let it run for a week. So you want to do some other things with your computer as well. So it's very good to implement the model in this way, that you can save the model and then later load the model and train it again and again. So now we have here the values of the loss function. In general, what would we like to see here? What development do we expect of our loss?
We expect it to go down.
Yes, we expect it to go down. If we would run a very simple neural network, and we see that the loss is increasing, like it is here, this would mean that we have made a big mistake, the learning rate was too high, and we are jumping out of an optimum. Why can it happen that the learning rate is increasing and the loss is increasing in our study?
Maybe the next batch was so different, like just...
Exactly, because we are taking batches, and the batches are just random samples of our observations. So we train the model on one batch, and then we take another batch, and the model might not really work well on this batch, and this is exactly what we want. So as long as in the end we see a kind of steady decrease in the loss, we are still fine, even if there are some points when the loss is increasing again. And here, right now it looks quite fine, so the absolute value is not important anymore. It's really about the relative values. You cannot say, I have a loss of 300 and this means this and this and this. It's totally depending on the data you feed into the model. So, but what we are seeing here is kind of decrease, at least now. So sometimes it goes up, more or less it goes down. If you have the impression that you are not learning anything, so the loss is not decreasing anymore, this can have different reasons. First reason would be the learning rate is too high. You should reduce the learning rate. If you are seeing a decrease, but the decrease is very, 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 very slow, you might increase the learning rate to make it faster. But then again, you have to see, is it still going down? So, what we would love to see is a point where the loss is not decreasing anymore. So you would love to see that these values go down, 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 and at a certain point they just are stable and don't change a lot. This would mean that we found a very cool optimum in data. Right now this doesn't look like an optimum. The opposite, we see a strong decrease in percentage in the learning rate. So probably to really train this model, we would need not only 2,000 iterations, but maybe 20,000, 200,000, or whatever. We don't know yet. But this doesn't look like we're finished. It looks like we're on a good way. It's probably not finished yet.
I have another question.
Yeah.
We have been talking about vectors and inputs, right? So you were telling us that it doesn't include always like a vector, zeros and one as an output respective. Okay, so you take it for every word.
So yeah.
And then you fit the one on this one.
Well, as I said, if you want to think about it, how what is going on, it means you take the skipgrams as observation. Each skipgram is an observation, and you have one word as an input and one word as an output. This is if you want to think about what really happens. But if you want to think what happens inside the computer and how to design this model, then you have to be aware about the dimensions of what you're putting as input and output. And the computer does not deal with the words. So what we did first is we were mapping the words to numbers. Yeah? But the computer does not take the number 5 as a number and calculates things with it. But what the computer does is it says, oh, we have 100,000 words in our vocabulary, so I make a vector with 100,000 entries, and the word 5 is now represented as a vector with 100,000 zeros, except the 5th place, which is a 1. And the same with the outputs. Yeah.
we are
nearly done, so we just could wait.
Yeah.
Some 300 steps. And this doesn't look so good anymore. Now it's increasing again 2 times in a row. We were already a lot lower. There might be a problem.
Could it be that the batch size is too small?
Of course, yeah. It could be the batch size is too small, or it could be that the batch size is yeah. Oh, this looks good again. So batch size too small could be a point, or it just could be that for the size of the batches we didn't run enough iterations. So it's very hard to judge from these numbers if everything is right or not, because you don't know what will happen if I continue doing this. You know, it might be that it oscillates on very high numbers and suddenly really drops. So it's not, normally you expect it to be a curve like this, but this is in real applications hardly never the case. So it could be that it's like an oscillator and then suddenly drops, and then you found your minimum. So this makes it really, really difficult. But here again, now it looks quite good. So we have now a loss of 200. We started with a loss of over 300, and we really decreased our loss. Let's see what we have here.
So if you go to the terminal, the command is, if you open the terminal to open tension.
And what was this? Just see.
It gets the
Yeah, okay. We can run this as well.
Okay.
So, just to see what we have different words. For example, and what kind of distance?
I think you check the distance.
To which version?
Good.
Yeah. Yeah. I entered the word as a seed word just to see what happens. So we just take the word gut, German for good, and then we just take some of the words that are now very close, taking the cosine distance function to our word good. And these are sprachliche Abgeordneten, Umsätze, Teuer, Abstimmung, Union, Administration, Coordination, and so on. And now we can do something that we haven't shown before. There were some lines in the code where, for example, the saver, where the model was saved. And not only the model was saved, but we saved different different variables. What we can do is we can now run TensorBoard, which is very cool function.
Denke einfach an den Terminal.
Ja, ich wollte es dir rüberziehen.
Nein, auf den Terminal, den Linux-Terminal.
Ich wollte es für dieses Terminal machen.
Weil ich habe direkt den Command.
Okay. Hast du das schon noch?
Ja, du kannst das schließen.
Okay. So what you have to do to start TensorBoard is
Ich mache Ctrl+C und dann einfach genau Open und dann kommt er.
okay. You have to say, of course, in which directory your model was saved, and then you just can run TensorBoard. So this has where do I find TensorFlow? In the bin directory there is the command TensorBoard, and now comes the directory where the model is. And if you put all this together, then run this command. something like this should happen. Found model, blah, 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 blah. And now the tensor board is running in the background. And now we can just take...
you need to open the link.
Just take a browser and go to local host. Yeah, 6006 for Google. 6006 for Google. And now we get some very interesting information. For example, we saved our loss. And we can see, oh, it really was decreasing all the time. And the decrease is not so it's like we want to see it, more or less. But perhaps if you would go on, it might decrease more. But this is just one visualization we have here. The more important visualization is if you open the TensorFlow projector. Where is it here? Because some sessions ago we already showed you that you can present all the word-to-vec vectors in, for example, two-dimensional space, which goes like this. You take the vector space, we have I think a 300-dimensional vector or 200, I'm not sure, and we can calculate PCA, principal component analysis, and then just take the first and the second principal component to map this in 2D, or in this case we take the first, the second and third principal component, and then we have a 3D representation of our vector space. And this looks, of course, very, very cool, but this is not the only thing about it that it looks cool, but you can use some very useful things with it. Where is it? Yeah. Oops. For example, we now can search for a word. Well, I don't know, what should I search for? Let's say, we just search for euro, and now we get all the words that are found with euro, and for example, we could say we take the word reading the word euro. So what we see here now is now we only see now we see still a lot of words, but now we can, for example, here we can define how many words we want to see. 200 words that are closest to the word euro, 100, and now we just can click on isolate the points, and now we get the 100 words that are closest to euro, and we can stop it turning if you want to have a view on it. So we have euro, the word euro is in a very close connection to the word WE-Vis, which is the civil service in Germany. It has some connections to the word entstehen, rücksichtslos. So some of these connections might be strange, others might really make sense. And what we can do now as well is...
But remember that the model is not finished training,
exactly.
So these results are not represented.
I'm just showing this to show you what you could do with a trained model in the visualization. So it doesn't really make so much sense in this case because the model is not finished training.
So
but
these are predictions?
no, what we did in the word-to-vec model is we were mapping every word into a 200-dimensional vector space.
So does it mean that here we see not the model results such as the statistics from the data we have?
No. these are the model results. It shows us in a three-dimensional space which words are closest in our model. So this is the idea. So the word euro often appears in the context Wehrdienst. Probably there is a combined word in Germany like Euro Wehrdienst or something like this. Or the model is not really trained. So if the model was trained, then now you could see very interesting correlations of the words. And you can even increase this by defining a custom space where you want to map the words. So for example, let's see, this is here. So first you say, what is the word? By name, so and we have the word euro, and now we can say on the left axis, we take now the vector, for example, for Deutschland. And on the right, we take the vector for Griechenland. Does it work? Yeah, it changed, yeah? I couldn't see it because the light was so now the idea is, the more you go to the right in this picture, to the left, the closer the words are to the word Germany. And the more you go to the right, the closer the words are to the word Griechenland, Greek. So, and we see, for example, the word euro here is closer to Germany in the parliamentary debates than to Greece. And in Greece we have words like catastrophe, umsetzen, nuclear.
Schlecht vernetztes Modell.
Do you have, are there any nuclear power plants in Greece? I don't know. Well, it could be because of, I don't know how old these protocols are. Chernobyl or something? I don't know. But probably just the model is not really trained so good. I would say we should run it 20,000 times or something like this. And then see what happens. Yeah, but you get the idea. Now you can make qualitative analysis of your word-to-vector model, and you even can add more dimensions. So then we have it on 4-dimensional space. Let's say we take the word Krieg at the top and freedom at the bottom. So, and again, it's not really, because the model is not trained. But for example, you see racismus is closer to war, racism is closer to war, and Israel is closer to peace. In this. Yeah, so these are the visualization. Any questions? Yeah.
Yes, as I have problems with saving right now, just tell me the command and what time.
So the command is just TensorFlow.
TensorFlow.
TensorBoard.
TensorBoard, okay.
I normally like to do it in another way. So I think the best, when you have it, when you have your code running in PyCharm, then you just can open directly a terminal here in PyCharm. By clicking on terminal, and then you are already in the right directory. So you just would, at least it works with
external computer.
Okay. So we get the terminal here. So we can your board. Let's see if it works like this. No,
Doesn't find it.
yeah. So we have to define our.
But your log directory is different than the directory where the model is.
Yeah. So we can't find the model because we're not in the log directory. So in the case of this computer,
But it's still nice because you can probably see the image nodes and not like all the nodes.
yeah, just play around. The idea is quite simple. Where is it? So here, the point is the comment you want to have is first of all you have to run TensorBoard, and it depends where you have installed TensorFlow. So the comment could be if TensorFlow is directly in your home directory installed, then it's /TensorFlow bin TensorBoard. And why did you set
Log diary.
log diary?
Log diary. But
So it's not full. Yeah, log diary. So you just specify your diary where you have saved your module.
Okay, so you have to run the TensorBoard command in the TensorFlow ordner with the parameter where, yeah, but it directly.
And sometimes it gives problems if you try to use a relative parameter here. So you should always take the whole path of the log directory. And then you should do something like this. And now TensorBoard is running in the background, and then you switch to browser and go to localhost 6006.
And could you tell if you need to break down the model training, how can we the code make it?
Yeah, you can find all this yourself. So this would be exactly what I planned for homework. If you want to do some homework, you have in the code, let's switch to the code. Everything here defined. Wait a minute. The model is saved. So what you have to do is you should just search perhaps in TensorFlow tutorials how to reload the model and keep on training it. And this would be very helpful. Shall we present the solution next week?
Just to play that myself, if you increase the range, in this case from 2,000 to probably 20,000, whatever, to 200,000, you are not going to overfit. You're just, in the end, you're just having two small steps, so you won't have any reduction to loss function.
we are overfitting, but the word2vec is overfitting. We are creating a space based on the words we have. So we want to overfit. We don't want to predict something when we train the word2vec model. We want to see how close the words or far away the words are in our documents.
So it's not getting worse, that's what I meant. So
It's more representative about your documents. Yeah.
So it's just getting
Better, the more you
More
train.
like-
Yeah.
In theory.
Then it depends where you want to apply the data, because if I train a model on the EU laws and I want to predict with this vector something about football, then it won't have a good predictive power probably, the model. because the vector of the words were trained in a political context. And then
Okay,
want
so
to
to have the best possible prediction, you would need then more or less infinite amount.
Exactly. So, for example, what Glove does, which we are going to see afterwards, it was trained in Wikipedia, I think, or in thousands of documents. So it can be the vectors to be as general as possible.
But this is a very interesting issue. On the one hand, it's quite good to have a huge corpus to train in one, because then a lot of possible contexts are trained within the model and so on. Yeah. On the other hand, you always have something that is very specific. If you think about scientific articles, for example, when you're knowing I'm reading a scientific article, you automatically are expecting different contexts of the words. Or just an example from politics, the mayor of Munich. Does anyone know who is the first mayor of Munich?
First.
The mayor of Munich.
Currently, not in general.
Yeah.
It's Peter Reiter.
Exactly. And Reiter is also a word that appears in Germany for rider. So if you would train a model, a very general model, you would always think in this political context that Reiter is somehow in a close connection to horses. And this would be wrong. So I think what in the end what probably is the solution of real natural language understanding is to have different models on different levels. You probably will work with a very, very general model, and then you will work with a very specific context models and put them on top of it. So this is what I think is right now the best way to deal with this. And it's a general problem if you, with rhetoric, normally you say the more the better. But this is never true, not in machine learning. It's the more you, the bigger your input is, the bigger is the probability that you get some strange noise into your model. So of course, if you have bigger corpus, then you have more context that you can analyze. The model could be more general, but if you just add more and more and more texts to your model, then what happens is that the connections in the word that are those skipgrams that are very often presented in the corpus, they get a very good representation, but skipgrams that are more seldom in the corpus, they get a very weak representation because, so do you get the idea? The point is you have more or less in a document, more or less the same set of skipgrams, and some skipgrams are very common and other skipgrams are very rare. And if you are adding more and more and more to the corpus, you probably get with each document more of the common skipgrams. And this might reduce the signal for all the other skipgrams dramatically. And this is why in the real applications of word-to-vec, we go back to inverse term frequency models. So we are weighting the words again in regards to the number of appearances in one document and overall groups. Okay, we prepared a second.
Should we make a break?
Yeah, I just want to we make a break now, but the big question now is, okay, why do we need this word-to-vec where we spend so many time? And the point is we wanted to show you can use this word-to-vec spaces for text classification. And this is the second script, and in this script we will cover the GRU architecture of deep learning. So we discussed it already theoretically, what a GRU network is, and then we have an implementation. So after the break, just try to go through the script, try to understand it, and we are happy to answer your questions.